Hello everyone. In this video I'm going to go over a few more examples of drawing both orbital diagrams and writing out the longhand electron configuration. I'm also going to introduce the noble gas or shorthand notation for electron configurations. Leading on from what we finished up with in class, writing the orbital diagram for oxygen, I've also drawn in here the orbital diagrams for fluorine with 9 electrons and neon with 10 electrons. In each case, the added electron is spin down, or a negative 1/2 spin, going into another one of the orbitals that only has 1 electron currently. And we see that the longhand notation for fluorine is 1s2, 2s2, 2p5. Remember that means in the 1s sublevel we have 2 electrons, in the 2s sublevel we have 2 electrons, and the 2p sublevel we have 5 electrons. And then similarly for neon, we have 1s2, 2s2, 2p6. The noble gas notation, or the shorthand notation, is used, just like the second name implies, as a way to write these electron configurations in a shorter way. All of them are based off of the noble gases, which remember are in group 18, the rightmost group on the periodic table. So the first of those noble gases is helium, and as we saw earlier in class today, helium has the electron configuration 1s2. Notice that the next 8 elements, lithium all the way through neon, all start with 1s2. And so as a shorthand, we can say that 1s2 is the configuration for helium, and use that to start the configuration for the larger atoms. So for example, for lithium, we would put He, the symbol for helium, in square brackets, and then 2s1. And so what that He in square brackets is saying is the electron configuration for lithium starts with the electron configuration for helium, and then we need to add in 2s1 after that. The only difference between lithium and helium is that extra electron in the 2s sublevel. Similarly, beryllium would be He in square brackets, then 2s2, and all the way through down to neon would be He in square brackets, 2s2, 2p6. If you look at your periodic table, you'll see that neon is another of the noble gases, and so if we go to the next largest element, sodium, which has 11 electrons, we would build up the orbital diagram same way that we have before. We start with the 1s sublevel, we put in a spin-up electron, then we fill the orbital, fill the sublevel I should say, with a spin-down electron. Similarly for the next sublevel that fills 2s, first we add a spin-up electron, then we finish the sublevel with a spin-down electron. After 2s comes 2p, which remember has 3 orbitals. So we would start by adding spin-up electrons to each of the 3 orbitals, then fill them with spin-down electrons. We've now filled the 2p sublevel, but we still need to add 1 more electron. So we need to go to the next sublevel, 3s, and we add a spin-up electron there to give us our full complement of 11 electrons. The longhand notation would be 1s2, 2s2, 2p6, 3s1. So again, indicating 2 electrons in the 1s level, 2 electrons in the 2p level, 6 electrons in the 2p level, and 1 electron in the 3s level. Now that we have the electron configuration for neon, whenever we talk about a larger atom in noble gas notation or shorthand notation, we always start with the most recent, or the noble gas that is just smaller. So here we don't want to start with helium, we can instead start with neon. So in the noble gas or shorthand notation, we start with Ne in square brackets for neon, and then the only thing that is new for sodium is we have that one electron in the 3s level. Skipping ahead a little bit, the next noble gas is argon, which has 18 electrons. If we look at the orbital diagram we drew for sodium, we can see we're going to have to go past the 3s level because we only have one more spot for an electron in 3s, but we have 7 more electrons we need to fit in. Following the Aufbau principle and the diagonal rule, after 3s, 3p gets filled. And remember, all of the p sublevels have 3 orbitals. So as we start from the beginning to fill in the 18 electrons for argon, we would put 2 electrons in 1s, 2 electrons in 2s, put 1 electron spin up in each of the 2p orbitals, then an electron spin down in each of the 2p orbitals. That gets us to 10 electrons. 11 and 12 fill the 3s sublevel, and then for the 3p, again, just like the 2p, we start according to Hund's rule by adding in single electrons to each orbital, and then filling in the second electron with the opposite spin in each orbital as we go. And so we see that 18 electrons fills up through the 3p sublevel. The longhand notation would be 1s2, 2s2, 2p6, 3s2, 3p6, or starting with neon, we then add 3s2, 3p6. And one thing you may notice is all the noble gases we've looked at so far, helium, neon, and argon, all end with 2 electrons filling an s orbital and 6 electrons filling a p orbital. And this is something that we'll come back to in the next couple of chapters as we tie in this electron configuration business to the periodic table and what each of the properties of the groups of the periodic table, and then going on to chemical bonding. There's something special about this combination at the end of 2 s electrons and 6 p electrons that gives the noble gases their great stability. We just want to look at a couple other larger ones. Remember, after 3p, according to the diagonal rule, is when we first start getting into something we might not expect. If we were to look at the next largest atom, potassium, with 19 electrons, the first 18 will fill up through the 3p sublevel, just like we saw for argon. But remember that if we follow the diagonal rule, the next sublevel that gets filled after 3p is 4s. And so we do not get to 3d until afterwards. We next go to 4s, and we add that last electron as a spin-up electron. The longhand notation would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, or in the shorthand notation, it is the argon configuration, and then 4s1. I'll just do one more example of these showing all three representations, the orbital diagram, the longhand notation, and the shorthand notation. And I will do it for scandium, which has atomic number 21. So when it's neutral, it has 21 electrons. So from what we have for potassium, we need to add another 2 electrons. Let's start by going through and filling the 4s orbital. Putting that second electron in the 4s sublevel gets us to 20 electrons. So we need to open up another sublevel. The diagonal rule tells us that the next sublevel is the 3d sublevel, which has 5 orbitals. So we draw out our 5 orbitals for the 3d sublevel, and our last, or 21st electron goes in as a spin up in the first of the 3d orbitals. One little subtlety when we do the longhand notation, even though 3d starts getting filled after 4s, when we write the longhand notation, we put all of the n equals 3 sublevels together. So it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, and then 4s2. Or in the shorthand notation, we have the argon configuration, then 3d1, then 4s2. For the quiz, there are a few different things you're going to be asked to do. The first is what we went over in class and the examples we just looked at. If you're given an element, you need to be able to draw the orbital diagram, write the longhand notation, and write the shorthand notation. So for example, if you think about what we just did for scandium, you need to be able to supply each of those 3 pieces of information. Again, remembering the 3 principles, the Pauli exclusion principle, the Aufbau principle shown by the diagonal rule, telling you what order the sublevels get filled in, and then Hund's rule telling us how we fill the different orbitals within a sublevel. One spin up electron into each orbital first before we start finishing off the orbitals by putting in a second spin down electron. We can also think about taking each of those pieces of information and going in the opposite direction. So for instance, if we could be given an orbital diagram and asked to identify the element, here we would do that by just counting electrons. So in the example that is shown, we have 6 electrons, and so we could look up on the periodic table that 6 electrons corresponds to carbon. Same idea if we're given longhand notation. Again, we can count electrons. Remember, the superscripts tell you how many electrons are in each sublevel. So if we add up all of those superscripts, 2 plus 2 plus 6 plus 2 plus 6 plus 10 plus 2 plus 4, we would get 34 electrons, which we would see is selenium. And then finally, same idea from shorthand notation. The one extra piece of information we need there is we need to see how many electrons are in the noble gas that we start the shorthand notation with. If we look up xenon, we would see that xenon has 54 electrons. And so the total number of electrons indicated by this shorthand notation is 54 plus 14 plus 2 plus 2, which is 72 electrons, which we see from the periodic table is hafnium.